Hello, my name is Eberhard Kuhn. I am the Marketing Manager for Food and Consumer Products at Shimadzu Scientific Instruments. I will be talking about food contact materials. Are they GRAS or are they GROS? The acronym GRAS, G-R-A-S, is often used in the food industry to indicate foods that are generally recognized as safe. G-R-A-S, GRAS, generally recognized as safe. Here's the outline to my talk. I will be describing the types of food packagings that are available as well as their purpose and function. Then I'll be giving you some definition of food contact articles, food contact materials, food contact substances, and so on, and briefly touch on the regulations. Then we will dive into the contaminants such as mineral oils, metals, organic, and PFAS. And finally sum it up and say, what does this all mean in terms of the food safety? On this slide, we see some examples of food contact materials or food packaging. Now, we all buy food, we all eat food, we all store food, so we are quite familiar with these. The food comes in glass jars, it could come in metal cans, in plastic or cardboard or paper kind of products, typically associated with the fast food industry, for instance. Then we have aluminum pans and things like that, metals, and of course the food storage, the plastic containers that we all use for our own food storage. Food packaging serves a number of purposes. First, it must protect the food. That means it must keep out moisture, it must keep away light, it must keep away pests and bugs, and at the same time it must keep in the flavor, it must keep in the nutrition and prevent spoilage. It must be sturdy enough to allow transportation of the food without damaging it, but it also must provide a surface where there can be information displayed, such as the nutritional information that we all look at, but also give a little bit of opportunity for the manufacturer to advertise their product and give us additional information. But what else comes in contact with our food? There's a long road, what is called the farm to fork, for instance. And so the food starts out on a farm as, say, a chicken or a pig or so, and then eventually ends up on your breakfast table as bacon and eggs. But along the way, it goes to a factory where it's being processed, it's being transported by trucks or trains. There is some containers that it's being stored in. There is the cookware that it's prepared in, and then finally the dishes that it's served on. So there's a lot of different things that come in contact with our food before we eat it. Now let's take a look at some definitions. There are government agencies like the European Food Safety Authority, EFSA, or the US Food and Drug Administration, FDA, that define certain food contact articles and materials. So a food contact material is a material that is intended to come in contact with food, and the key word here being intended. So from the beginning, it is designed to come in contact with food, which means it is subject to certain regulations. Now, those food contact materials include packaging, containers, kitchen equipment, and so forth. The challenge is that they are made from a variety of different materials, such as plastics, rubber, paper, glass, wood, metal, and so forth. Anything that's used in the processing equipment, but also includes things like coffee makers, where you have the glass carafe and the plastic filter holder and so forth, and sometimes even includes the ink that's used for labeling. Now, there are also food contact substances, and those are substances that are used as components of the food contact materials. But instead of looking at these definitions, let me give you some examples of what these compounds are. So now let's look at a specific example. Starting on the left, we have a jar of Nutella. So that jar is called a food contact article because it is the complete article as you would buy it in the store. Now that food contact article is made up of a number of different food contact materials. In the case of the Nutella, it is a glass jar that has a thin metal foil on top to preserve the freshness, and although it's not shown in the picture, there is actually a plastic lid that goes on top of that. So this food contact article is made up of 3 different food contact materials: glass, metal, and plastic. The food contact materials in terms are made up of food contact substances, such as monomers, polymers, solvents, additives, and so forth. And specific examples of those would be the PFAS, mineral oil, phthalates, bisphenols, and so forth, but also the metals such as lead and chromium. And one final term or acronym that you might hear, which is the non-intentionally added substances, NIAS. Of course, there are also intentionally added substances, but the focus is on the non-intentionally added substances because those are the ones we are looking for and the ones we don't know. They're the unknowns, and they can migrate into the food from the food contact materials. And they could be things like unreacted monomers, they could be degradation products and things of that nature. I don't want to go too deep into the regulations other than show you that there are regulations in place and you can look them up if you're interested in the details. Often those are 100 pages long, so they would take quite a while to discuss here. So I just wanted to show you that there are regulations in place both in Europe and in the US. As is often the case, the EU leads the way in such activities, and back in 2013, the EU Commission already announced that there'll be some activities towards regulating food contact materials. And in fact, this year, countries like Denmark are planning to entirely ban PFAS in paper and cardboard materials. And here in the US, even presidential hopefuls are taking time out of their busy campaigning schedule to submit bills that would ban PFAS in food packaging. And the state of Washington, for instance, has identified priority products such as bisphenols in cans or printing ink as priority products. The military is starting to restrict PFAS in military food packaging, and in fact the FDA has recently released a PFAS method for analyzing PFAS in food and will finalize the method very soon. But enough about regulations. Let's look at some real science. First, let's look at the mineral oil hydrocarbons in food packaging. There are two fractions, the MOSH and the MOAH fraction, the mineral oil saturated hydrocarbons and the mineral oil aromatic hydrocarbons. It's the latter one that includes some potentially mutagenic and carcinogenic constituents, and that's the one we want to focus on, and they do make up to a third of the entire mineral oil fraction. The analytical challenge is that there are many different compounds within the MOSH and MOAH fragments, as you will recall from your organic chemistry. If you take 5, 6, 8 carbon atoms, you can combine them in any number of different structures and isomers. So both the MOSH and MOAH fractions literally have hundreds and thousands of different compounds. As we can see here, the levels of MOSH, MOAH, and mineral oils in foods can be quite high, and even in food contact materials such as paper and cardboard, we see a very significant amount of mineral oils residue. So where are these mineral oils coming from? Well, there are multiple sources. They can come from the packaging material that includes the recycled paper and some of the ink that's used on labeling the foods. But also anytime there is a machine involved in processing the food, like the one shown here in the picture, or a harvesting machine, so anything that requires a grease or lubricant to function. But also food additives such as separating agent, coating agents, and things of that nature. And also let's not forget that the environment contributes to the food contamination as well. So exhaust fumes from cars can also be a source of mineral oils. In these chromatograms, we see the contribution of the food packaging to the food, where we have a jute bag that has been processed, and then there's what's called a batching oil that is used in the manufacture of the bag, and that batching oil is then transferred onto the rice, and so then it ends up in our food. Here we see the Shimadzu automated LCGC online system. It consists of a normal phase HPLC that is connected via an interface to a dual column GC system and allows for some additional sample preparation through some additional instrumentation. The HPLC separates the MOSH and the MOAH fragments, and you can see here that the MOSH will elute first, followed by the MOAH, and then those fragments are transferred onto the dual column GC. And the dual column GC then identifies each of the different components within the MOSH and the MOAH fragments further and compares them to the internal standards. Now let's switch gears and look at some heavy metals in food packaging. For this experiment, we went to our local supermarket and we bought 3 types of food containers: polystyrene, polypropylene, and polyethylene. We then used what's called food simulants to leach the whatever is in these food contact materials into the food simulant, and then we analyzed for 14 heavy metals simultaneously with a high sensitivity Shimadzu ICP-MS 2030. And here we see a summary of the data for the 3 different types of food containers: the polystyrene, the polypropylene, and polyethylene. On the very right column, we see the method detection limit, and we see that the method is indeed very sensitive, often in the sub-parts per trillion level. We see that some of the more toxic elements, such as cadmium or lead, we see very, very small amounts, and others like aluminum at a much higher level. This table shows a comparison of the 3 types of food simulants that we used, and you can see here that in the acidic food simulants we get a higher amount of metal extraction than in just the ionized water. So the conclusions are, the good news is that all the detected amounts were below the limits defined by the European Union. We also saw that there were some differences depending on the types of plastic and also on the type of food simulants we used. And while we didn't show the data, it should not be a surprise that there is a correlation to the contact time, with longer contact time leading to higher amounts of material. In our next experiment, we were looking at extractable organics from food packaging. Again, we went to the local market and we bought 3 types of food packaging: a plastic bag, a plastic cup, and some aluminum foil. The samples again were extracted with water and some other food simulants, but in this case they were analyzed on a Shimadzu LCMS 9030 QTOF, scanning from 100 to 2000 M/Z. Using some special features of the Lab Solutions software, we were able to identify a number of different contaminants in the different food contact materials using the different food simulants. Using the Shimadzu Insight Explorer and Lab Solutions browser, we were able to screen these ions and identify 19 unknown ions from both positive and negative modes. We were then able to further confirm these ions by looking at the fragmentation data and comparing them to a commercial library, such as the Medlin library for MSMS. And the similar fragmentation patterns between the unknowns and the database basically confirmed the identification of those compounds. The data I showed you are just a few of the possible contaminants in food packaging. There are others, such as UV stabilizers like benzophenone, residual solvents, of course, and chlorates, perchlorates from disinfecting processes, and of course PFAS. Shimadzu does have a number of application notes and data available on these materials, so please take a look at our website for more information. Some people have actually done migration modeling, such as, if you look at the bottom, there's a link to the Food Packaging Forum that has done some of this migration modeling. And for that modeling, they have looked at things like the time of contact, the temperature of contact. So for instance, if you take a look at that picture of the hot coffee, that hot coffee will extract more of the food contact materials than, say, an iced tea. Other things like the type of food contact materials, and the surface to volume ratio were also studied as part of this migration modeling. There is a label that you can look for. There's just this glass and fork that is a symbol for safe food. PFAS has received a lot of attention in recent years, and it's often called the forever chemical because it doesn't degrade or anything. It stays around forever. But I also call it the wherever chemical because wherever you look, you will find PFAS, anywhere from drinking water to food containers to food cooking ware, for instance, or this bag of popcorn that's on the inside. Because the PFAS, of course, the material itself is great because it's both water repellent and grease resistant. So it does both water and grease at the same time. So it is a very good material, which is why it's being used so heavily in the food industry. So what are PFAS? PFAS are a family of compounds that are per- and polyfluoroalkyl substances. And in the past, sometimes they've been called PFCs, perfluorinated chemicals. And there's a whole variety of these materials. And it's not only the PFOA and the PFOS, or the perfluorooctanoic acid, or the perfluorooctane sulfanoic acid, but there's a whole variety. These are the most common ones that have been studied, but there are in fact hundreds and thousands of different kinds of PFAS, short chain and long chain, which makes the analysis quite challenging. Now let's take a look at how PFAS could end up in our food. PFAS has been in the news for some time, and it started out primarily as an environmental concern. But as you can see through this graphic here, it does end up in the food supply. So we have here three color-coded routes. We have the sources that are in yellow or orange. Then we have the route of the PFAS in green, and finally the exposure to humans in blue. And as you can see from the PFAS manufacturing, it goes into the textiles, the cookware, the food packaging. And then of course from the cookware and food packaging, it's directly transferred onto the food and then consumed by the people. But it also, a lot of PFAS is used in the firefighting foams, and when those are dispensed into the environment, they could end up in the surface water, which is then used to irrigate farms. So the PFAS ends up in the farm animals, and then we end up eating those animals, so we eat the PFAS. And it also ends up in irrigation of the produce, and again, we end up eating that produce. So we end up consuming the PFAS that comes from the environment, as well as the PFAS that is directly used in products in cooking. For the analysis of PFAS, Shimadzu offers a number of solutions, mostly based on our LCMS triple quad platforms. If you are using a method that requires a solid phase extraction, then our recommended solutions is the LCMS 8045 or the LCMS 8050 to use. If the method allows for direct injection, then the LCMS 8050 and LCMS 8060 are the recommended triple quad platforms. Recently, we conducted a study on looking at PFAS in bottled water by direct injection, and we had different types of materials. We had a glass bottle. We had, of course, different types of plastic bottles, including the recycled plastic. We had some metal cans and a cardboard, like a milk carton kind of container for water. You can see here in the table that the good news is that in most of the samples we looked at, we didn't see or quantitate any kind of PFAS. Our method detection limit was around 5 parts per trillion, and we only saw two of the PFAS, the PFBA and the 6,2-FTS, in a few of the samples. So where does that leave us? Is there such a thing as a GRAS food container? I recently hosted a networking session on food contact materials, and the consensus opinion by some of these industry experts that were present there was that glass was in fact the most GRAS food container. It can be cleaned more readily, but also just inherently glass is one of the purest substances when it comes to being a food container. The other question is, are today's safe solutions, will they still be considered safe tomorrow? Well, we only know today what we know today. So in terms of the impact that a safe solution today will have, we don't know. There's an incubation period, if you will, of years or decades sometimes before we see any negative health effect on any kind of safe solution that we have today. And an example is, recycling. We all recycle, and recycling is a very good thing. However, it presents some challenges when it comes to food contact materials, because the food contact material that are on the outside, for instance, the ink or so, that's a contaminant. In the recycling process, it can now become part of the actual material and then migrate into the food. So we are introducing contaminants through the recycling process. Now, the recycling industry, and I have to admit I don't know anything about the recycling processes in detail, but they assure me that they have processes in place to remove these contaminants so that they don't end up in the recycled products and then migrate into the food. I want to leave you with a more positive image of food. We talked a lot about the food contamination and everything, and yes, there is contamination, but that shouldn't prevent you from still enjoying a glass of wine or having some bread and cheese and still enjoying your food. I want to thank you for listening to the webinar today. I hope you found some of the information interesting and useful. If you have any additional questions, don't hesitate to email me at erkuhn@shimatsu.com. I'll be happy to answer your question or start any kind of dialogue or communication with you. Have a nice day.